Okay, now we have over 30 attendees, and I'm sure the number is still growing. So it's 2:02 now, let's get started. So hello everyone, welcome everyone to Ask Seminar Series. This is John, the seminar speaker. I will be moderating the seminar with Cassie, who is our communication manager. Just so you know that the seminar is being recorded and we will publish the recording on our YouTube channel. And this is a kickoff seminar of this spring. And we have a very great lineup of the speakers. We have Professor Lee here, and we also have many other outstanding speakers. So please stay tuned. We encourage you to bring up any questions after the presentation. You can do so by unmuting yourself and ask verbal questions. Before the speaker gets started, I'm going to hand this ball over to Prof. Our Associate Director. And just so you know that our Director, Naz Peter, is also joining us. Prof, please proceed.
Yes, yeah, thanks, John. And I won't take too long, but I'd like to introduce our speaker, Professor Lee. She's at the Department of Civil and Environmental Engineering at Penn State, focuses on the intersection of ecology and hydrology and biochemistry, and looking at challenges with inland water. Let's see, she's AGU fellow. She received a couple of recognitions at the AGU in hydrology, and she got her PhD from Princeton and has her other degrees from Nanjing University. And this is a really interesting topic. We actually had we have a small project going here at the University of Maryland, and water quality is one of those things. And we're looking at rivers and the Bay and DC, Washington, DC, and neighboring Montgomery County get their water from Potomac River. And so we have some scientists at ESSEC that are looking at that water quality. So anyway, I turn it over.
Thank you so much, Prof.
Yep.
Let me share my screen. Okay. Okay, thank you so much, Prof, for the introduction, and John and Cassie for having me here. I'm very excited about this opportunity to give a talk on river water quality in Earth System Science Interdisciplinary Center, which I have been talking before. So thank you for having me here. So first of all, most of the work from my group is funded by National Science Foundation, multiple generation of critical zone observatories, and also Department of Energy, Office of Science, Earth System Science. So these are my major funding sources. I want to, I recognize that I'm giving the talk here, but this is really, a lot of work that I present here is coming out of collaborative work with students, with collaborators from different universities, which I don't have time to introduce individual, but I'm really grateful for the opportunity to work with them for their inspirations with ideas, data and questions, but also all the fun and friendships they bring together with all the soil pits we digged, with a lot of river and stream and hills we walked. So this is very special to me. In addition to the science, it's really a privilege to work with them. And I also want to kind of putting a plug-in for my seminar series, which is Women Advancing River Research. It started during the pandemic. It happens every third Thursday each month, except December. at 11 a.m. US Eastern, so you can use the barcode to register and to join. Usually, every time we have 2 speakers and it features women scientists from all over the globe. So this is something that we have been running in its 5th year. There's also recordings for the videos as well. So let's talk about water. Water is something that defines our pale blue dot, essentially. And if we think about rivers, we have human as a species have long settled around river and streams since we were hunters and gatherers. Today, we build huge cities around these rivers and streams. So if you look at global data, there's roughly 90% of global population live less than 10 kilometers from a freshwater body. So if you think about rivers, they are connections, it's a connection, it's many different things, right? It's a meeting place, it's entertainment, it's inspiration, it's also home to us. So rivers mean a lot to us. And if we think about, the most close relationship with rivers, you can ask, where does your tap water coming from? Surface water, including river and stream, lakes, reservoirs, in average provide 60% of source water. And this water goes through complicated treatment processes like filtration, coagulation, filtration, disinfection, many different processes in drinking water treatment plants before they are distributed to our homes, to industries, etc. So rivers are very important to us. And river quality is really about what's in water. And there's many different measures of water quality. There's physical conditions like water temperature, chemical and biological conditions. So there are many things, dissolved oxygen, turbidity. There's also nutrients, carbon, dissolved organic carbon, dissolved inorganic carbon. These are very important chemicals. Also particular carbon, and then many different things, salinity, PFAS. If you look at the USGS website about what they measure in terms of water quality variables, there's thousands of different things coming up. So this is just a major group of what we think about water quality. And clean water is very expensive. We think about, since 1972, when the Clean Water Act in US coming into effect, in the US, we have already spent $5 trillion in terms of cleaning water. So this is about 0.8% of GDP or $400 per US citizen per year. So clean water is very, very expensive. It's very most expensive environmental investment, more than clean air, actually. Now, the access to clean water is very limited. If you look at the global population, more than half of the global population lacks safe drinking water, especially the global south. These yellow colors indicating around 20% of the population have access to safe drinking water, which is very low number. And it's water quality is so much more about, it's not only about human consumption, it's also about climate feedback. For example, a lot of carbon or nutrients in the water can lead to greenhouse gas emission, climate feedback, etc. There's ecosystem health in terms of fishes, a lot of aquatic life, water temperature, dissolved oxygen, pH, turbidity, they're all important to aquatic life. In terms of food production, for example, salinity is a huge variable that will control soil health, and soil properties would affect the yield of crops. Energy production, the water temperature, energy production depends on things like hot water, cool water to cool down the system to have efficient energy production. So water temperature is a very important variable for energy production. And also we know that river water quality has been increasingly threatened by climate change, especially in terms of climate extremes like droughts, heat waves, rainstorms, floods. There's a global survey coming out a couple of years ago looking at these climate extreme effect, and they have summarized in most cases water quality degrade under climate extremes on top of the baseline change in terms of average warming climate. Interestingly, the river water quality hasn't been getting much attention in the climate risk assessment. If you look at all the chapters in the most recent IPCC report, there are a lot of discussion about water quantity, water cycle, and for example, global carbon or water quality in oceans, but not inland water quality. So this comes to in the water quality community, we think about that as invisible water crisis, probably because water quality is harder to see, not like water quantity. It's you can see how much is there, how much is changing, but it's much harder to see water quantity, except a few variables. So water climate risk related to inland water quality degradation have been largely overlooked, and this need to get more attention. So along that line, one of my goal in the first part of the talk is to show how has river water quality changed in warming climate, and then there's other parts we will be thinking about what drives water quality change. And at last, the last question, I'm hoping to have a little bit of discussion about how can remote sensing help, because this is ESSIC is very much, there's a lot of remote sensing experts. So maybe we can get some interest in terms of thinking about river water quality in more depth or more broadly. So along this line, these questions is in parallel, they're also kind of like talking about two types of model. One is a deep learning model, which is more kind of somewhere related to correlation, looking at the patterns, temporal trend. But then there's the other type of model, which we call traditional process-based reaction transfer models, that help us to think about what are the mechanism processes that leads to changes in water quality. So the first part of the talk is really about how much river water quality has changed in a warming climate. Now, perception, like we tend to have this perception that river water quality is more influenced by land use than changing climate. And I think the other aspect is that also river water quality have much less data than, for example, stream flow. So these two figures really comparing stream flow globally and water quality variable in terms of data, the spatial distribution and how they have evolved over time. You look at the 5 or 6 most available water quality variables stacked together, it's getting a bit of like closer to the similar magnitude as the stream flow. And if we look at all the water quality data, it's essentially about 2% of the time we have water quality variable measurement. That means about a week in a year, we have a water quality measurement, and in different places, they would have, usually we have different time periods of measurement. You could have one side, have measurement in 1980s and another have measurement in 2020. So huge data gaps, and they tend to be very spatially and temporally inconsistent, which make large-scale analysis very difficult. And this could be another reason that leads to, overlooked at the, climate risk assessment related to river water quality. And the measurements, the reason data are so scarce, a lot of time, we think about traditional water quality measurement, sensor measurement are relatively limited. We can do typically about 5 different variables, 5 to 6 different variables. So there are sensor measurements, but are relatively limited. Usually we go out, take water samples and bring them back to measure in labs using these big machines like ICP-MS and ion chromatography, things like that. So they tend to be very expensive, time consuming, and that leads to a lot of data scarcity issues. So related to that, this recent development of deep learning models, there's in terms of applying these deep learning models in terms of understanding the trend and patterns. So in hydrology application, deep learning models have exploded in the past several years, but for water quality measures, it has been much less. And when we talk about the deep learning models, is essentially, they're characterized by multiple hidden layers between input and output layers. This gives them advantage of learn complex patterns, but the disadvantage is they tend to be data greedy, like they need a lot of data to train the model, to train robust models. So water quality application in deep learning application in water quality has just started. So if this is something you are interested in, it will be the right time to jump in. I want to talk a little bit about the deep learning model we use, which is long short-term memory model. So it's a recurrent neural network model. It can retain time dependence of data. So it's good at reconstruct time series data, like it has been used for speech recognition, natural language processing, etc. So for this type of using this type of model, we essentially, how we use is compile a lot of time series data from different sites, and this is showing for US. So this particular example for dissolved oxygen, how much oxygen is dissolved in water, they're very important for aquatic life. So you can see, the target data tend to be kind of sparsely distributed, but we compile data for many hundreds of sites. And then we also use hydrometeorology data from the different sites. On top of that, there's also basin attributes data, which can be used as almost like the labels for different sites. It labels different characteristics of different sites. They include things like soil properties, mean climate conditions, land use, and land cover, things like that. So with all the data compiled, then we can, if we can train a robust model, it can be used for data, it's a gap filling essentially, right? You can see the data in the points, but then the model will fill up the blank space, knowing, so we have numbers, essentially we get daily numbers for each of the site, which allows to have consistent numbers to analyze temporal trend and spatial patterns. There's a lot of other application, for example, spatial filling in terms of prediction in engaged basins or predicting into the future. These I wouldn't have time to talk about, but this is, general idea is it fills the gaps. So I'm going to focus on most of the next few slides talking about 3 variables: water temperature, dissolved oxygen, and total phosphorus. They are among the most available data. This is work done, led by my previous postdoc, Dr. Wei Zhi. He is now in Hohai University in China. So this is among the most available data, so we can use deep learning model to apply and then to figure out the patterns, etc. So what I'm showing here is essentially about about 800 sites from 1980 to 2020, and this is we essentially trained both water temperature data and dissolved oxygen data. So and then analyze from the model output, we analyze for each site the trend in terms of river warming and the trend in oxygen loss. So this analysis shows that warming has occurred in more than 87% of rivers. And if we look at where things are happening most in term different land uses, Urban sites tend to warming up fastest, which is not surprising, followed by undeveloped sites, which is minimally impacted by human. And then there's a mixed sites followed by agricultural rivers. So agricultural rivers are warming up the slowest. Excuse me, more or less because there's a lot of irrigation activity, so they tend to cool the air more than other places, and also cools the water. So they are warming up the slowest. But interestingly, if you look at oxygen loss, overall, there's more than 70% of the sites have oxygen loss in terms if you look at the trend. And interestingly, also agriculture rivers, in the previous slide, we saw the slowest rate of warming, but it actually has the highest rate of oxygen loss, possibly because there's a lot of much higher nutrient level in agricultural rivers, so leads to a lot of biogeochemical activities that could reduce oxygen level. And again, undeveloped sites also see significant trend in terms of oxygen loss. So these are for temperature and dissolved oxygen. For total phosphorus, which is an important nutrient, not only for water quality, but also from the sustainability perspective, it's important because phosphorus has relatively limited sources on Earth, not like nitrogen. So for total phosphorus, we have seen declining concentrations in more than 60% of sites. And actually, urban sites have been doing really well in terms of decreasing concentration. Agricultural sites are still increasing because usually we do a lot of input on the land. But the other side of it is even with more than 60% of declining, more than 60% of sites with declining concentrations, more than 40% of sites still have increasing fluxes. So fluxes it's also sometimes we call load. It's concentration times stream flow. So it's how much it's in the units of mass per time, meaning how much mass of the chemical getting into river and stream. So there's still increasing fluxes getting into the stream. And we can tie back to, for example, increasing discharge. Like a lot of sites in agricultural sites, there's a lot of increase in river discharge in the recent years. So they have 17% per decade versus other places like urban or undeveloped that has a much smaller increase in terms of discharge. So overall declining concentration, but still a lot of increasing fluxes. So to summarize, these are kind of direct data supporting, river water quality has changed. And we see widespread river warming, oxygen, and nutrient loss, even in rivers with minimal human impact, meaning undeveloped sites. But land use does make a difference in terms of the rate of warming, right? It's fastest warming urban rivers, slowest in agricultural rivers. And it's fastest in oxygen loss and phosphorus loss in agricultural rivers. If we think about all these applications, mostly they are for more data available variables, including water temperature, dissolved oxygen, and total phosphorus. We actually did try for other soils, for example, nitrate and dissolved organic carbon at the continental scale. It was not as successful because of less data. And typical application, I mentioned temporal and spatial filling, also casting for the future or the past. And they give us, patterns, but not processes. So that leads to the second part of my talk, which is thinking about what are the drivers and processes that shape river water quality. Only understand patterns, sometimes it's not as satisfying. So this will be getting to thinking of using process-based rapid transfer model than thinking about traditional these differential equations, solving differential equations. I do want to step back a bit and think a little bit broader than numerical models because, in terms of model, sometimes we think about numerical models a lot in scientific field, but the models are really, in general, our perception of how the world works. It's essentially a collection, they are collections of hypotheses, assumptions, and knowledge. So if we look at the books and literature, there's a lot of different models into model creativity, model heroes, is many different examples. And if we think about models, they are really kind of it's part of our everyday life. Everyone is a model, right? We are doing a whole life model evaluation. If you think about that way, if you think about how we grew up, you might be, taking toys from a friend without their permission, and they are very upset with it. They're like, I'm not going to play with you anymore. So you integrate that information, you realize this is not something that people are happy with. You integrate that information, you modify your model, and then you learn to get along with other people. You learn to interact with people, and this is a key. It's an evolving process, right? That's how we learn to, is how we grow up, how we learn to do things. So these are essential hypothesis testing. And if we think about, if the different models are really is not exactly physical reality, right? Because everyone experiences different aspects life, and the truth is varies as many different as reality has many different aspects. It's very complicated. So in a way, our truth, my truth will be different from your truth. Its truth is a matter of imagination, as Ursula Le Guin has put it this way. And if we think of numerical model or system models, right, we put certain processes in that we think are important. So in a way, models are a work of fiction. We use models to understand certain aspects and answer certain questions, but they are not reality. So in a way, we use models kind of like writers use novels or fictions. They are not reality, but they resonate with reality, or resonate with nature, and they ask deep questions about humanity, society, things like that. But they are not a real thing, like Naomi Oreskes put it. So I'm putting this, up here because later I'm going to talk about different type of model and how we can use different type of model to answer different questions. Now back to river water quality, what are the drivers and the processes that shape river water quality? We tend to think about two major drivers. One is external forcing, right? You think about climate, long-term weather, short-term, day-to-day variation in terms of weather, but also human forcing, right? It's changes in land use. You put things in different quantities, things like that, or change the structure. The other is internal structure, which is including, for example, above ground landscape structure and below ground subsurface structure. These, in a way, it's almost like personalities, right? They modulate how the system respond to external forcings. And also the process going through, different water flow paths because of different structure, and eventually affect how they show, what kind of water chemistry show up in river and stream. So they have very different, you could see very different thing, depends on the structure of a system. In general, we tend to measure these water, stream flow and water chemistry in these different places, and then plot them in terms of we call concentration discharge relationship. So they are paired, and you can see how they, the concentration vary with discharge. That give us information about how responsive concentration are to changes in discharge. But also use that, we can calculate what we call load, which I talked a bit earlier, is concentration time discharge Q, which is another very important measure of water quality. So to understand the process, usually we use Rack transfer models. Rack transfer models here is like Rack transfer model 101, essentially. We follow the principles of mass conservation. If we follow an arbitrary solute I in water, you can see the left-hand side is essentially mass change rate in water. So water volume, time concentration, how much mass per time, right? Mass per time is depend on three major processes. One is the diffusive dispersive transport is the first term. And then, so this is more like local homogenization process. The second term, the advective transport, is essentially how fast water is carrying the solute, like move it from one place to another place, right? And then there's a reaction. That reaction can be multiple terms. One individual solute can react with multiple materials and can have multiple reaction happening. So there's reaction stoichiometrics, there's reaction thermodynamics, kinetics, all these folded in this kind of summation term. And with that, and if we also have initial condition, boundary conditions, that will give you concentration of this solute I in time and space. So essentially you follow the solute I in different time and follow it where and when it happens and high and lows, etc. In my reaction transfer modeling class, I often say we can use a reaction transfer model to trace, your life trajectory. If you think about, for example, dispersive transport is something like, for example, the local influence of people, right? You talk to a friend, you talk to your parents, they would have certain views that influence, you interact with it enough, there's a certain homogenization of how they influence you in terms of doing things, right? So that's the local homogenization effect. Advective transport is kind of like cultural, political environments, the bigger environments that would shape how you do things. And then reactions are, in a way, it's your passion, motivation, what excites you, what not excite you, all these, personality, all these would affect how you interact with other people. So in a way, they are very relatable. So when we think about reaction transfer models, is traditionally reaction transfer models are typically, they were started developed in 1980s. And it's mostly for subsurface processes. So it has more applications in hydrogeology, hydrogeochemistry field. In recent years, mostly in the past decade, we have this, critical zone observatory, and there's this need of integrating processes we call from the definition of critical zone is essentially from the treetop to the bottom groundwater. So essentially we need to think about the whole kind of array of processes happening, which is essentially, you need to integrate many different processes from hydrometeorology to watershed hydrology, how water moves through the system, how much plants take water away, ecohydrology. And then on top of that, the aquatic and soil biogeochemistry is where reaction happens and release out chemicals. So the more recent catchment scale reaction transfer model is kind of more, interdisciplinary in terms of integrating these different area of disciplines. And there could be multiple models. As I mentioned earlier, we're thinking about models are not physical reality. They are representing certain aspects of the system that, and it's essentially certain perspectives, certain angles that help us answer certain questions. So here I'm going to relatively talk about three different models with different model complexity, and with, again, that come with it would be, different computational data needs, but also different accessibility. You think about people have different background, and what their focus is asking question about, for example, different in terms of climate forcing versus structure, different aspect structure. So the first question in that slide is, if we think about how does climate control river chemistry, we can think about, looking down, we can look at watersheds. The simplest reactive transport system possible is one box watershed reactor. We don't think about the individual, like in detail structure in the watershed, but you are really looking at mass balance, right? How much mass coming out, how much mass coming out, in and out, and then how much reaction happening in the system. And with that, we actually can get, these long-term mean concentration, which is reflecting the climate, and get an analytical solution, which is mean concentration equals to the relative magnitude of rate of solute addition to solute export. So you could have a system, for example, under a climate zone, let's say in relative humid climate, you could have a lot of solute addition, but your solute export from, because there's a lot of water going through, right? So the export might be far more than solute addition, so it could lead lower mean concentration. Or if, in an arid environment, you might have very little solute addition, but the export is even smaller. So that leads to, potentially much higher concentrations. So this is essentially showing that if you look at in the global scale, not global, so US, continent, Kona scale, stream flow, we see that the great highest, or not highest, lowest stream flow, driest place is in the Great Plains. So they have these small stream flow bubbles. These are all mean. And they have the largest bubble for sodium, which is one of the solids dissolving out from the rocks. It can also come from salts and everything. But in any case, if you plot them on Bidoukou curve, you will see bigger bubbles, meaning in more arid places, you see higher concentration. And high concentration means lower water quality, because usually we don't want a lot of solutes in the water. That means heavy treatment burden, things like that. And these are for, coming off from the Campbell's CAM data set, which is built upon the Campbell's hydrology data set. And then if you plot, mean concentration versus mean Q, you essentially see that pattern of higher mean Q, mean more humid places, you see much lower concentration compared to more arid place, high concentration. And it turned out this is not just for sodium, it's for all the 18 solutes in Campbell's CAM. They all look this type of, we call dilution pattern, concentration decrease with discharge. Which indicating, usually the water quality in more arid places are lower, because usually you will see high concentration in all kinds of solutes. But also it means in places become more arid. That's happening in a lot of places. In places become more arid, the water quality is decreasing over time when they become more arid. So that's looking at really the climate impact on mean long-term concentration. Now, another question we can also look at is, what is the role of landscape structure? So landscape structure is something that we see easily, right? We can see all kinds, topography, land cover in different places, and you can essentially build these really complicated, we call spatially explicit models. You then divide, the watershed in different grids, hundreds or even thousands of grids, and then looking at these, how they are spatially distributed, solve for these. And that's something we did early on for Shoal Hills, is one of the Pennsylvania sites very close to us, one of the critical zone observatories. The interesting thing is that in the traditional, so we essentially followed the typical watershed hydrology model, usually have one surface flow path and one subsurface flow path. So it doesn't differentiate, different subsurface structure. And with that, we calibrate with the data we have in soil water, in stream water, you can get concentration, different variables in different time and different space, right? So different time of the year, this is a whole, like looking down at the watershed, you can get soil temperature, soil moisture, hydrological connected zones, and also rates of DOC production. So I'm focusing on DOC, which is dissolved organic carbon, which is one of the very important water quality variables. It could lead to, we call water browning, if there's a lot of high concentration of DOC. And in recent years, in past 2-3 decades, there has been a lot of more browning happening all over the globe. So this model allows us to look at production rate, but also actually concentration of DOC I didn't show. But this gives you essentially spatial distribution, and you can see these more hydrologically connected, also lower, like almost like valley part of the watershed. You see more high erection, high rates erection happening, and usually also high concentration as well. So these are hotspots of DOC production. If you integrate the whole watershed, and look in time scale, you can see a lot of things as well, like soil temperature, discharge. This is from April to April in 1 year. So increasing temperature, summer is high, and then decreasing temperature, and discharge is kind of like the pulses, right? Post disturbance getting into the system. So if you look at the production rate, which is in red, essentially it follows this soil temperature pattern. And then the export rate is how much material is flushing out of the system, is following this, pulses, right? So every time you have a big storm events or discharge events, you will see, first of all, DOC production, DOC build up in the system over time, especially in the summer because rates are high at that time. And every time you have a big storm event, it will the level of DOC will drop quickly. Yeah, and so over time it goes back at the end, go back to the relatively close to the original level. So that's another year begins. So essentially, the production happens mostly more in the summer, but export really follows the hydrology of the system. And so that's, for our Show Hill site, things work out really well for that site. And we try to use this to produce, to think about concentration, the different site for another site, which is a Colorado site, and which is a beautiful site, high elevation mountain about 3,000 meters high, snow dominated. And this site has this beautiful data in terms of concentration discharge relation, very contrasting, for a lot of biogenic soils like dissolved organic carbon or nutrients. They always follow what do we call it, flushing patterns, increasing with discharge. And for geogenic soils, things like calcium, magnesium, sodium coming more from weathering material like rocks, they all follow these kind of dilution patterns. So we really want to reproduce it. It's super interesting. What is controlling that? And we were using the models that I just talked about, and it keep on producing these very flat patterns that is not representing what showed up in data at all. And we were very puzzled for a long time until we saw a data set in Show Hills that have both soil water chemistry and groundwater chemistry, and we realized there's very different concentration level for different species, for different soils. And we realized that we might need to put multiple flow paths in the system in order to represent that, because what's show up in the river and stream are actually reflecting what's the subsurface processes. So we added another subsurface flow path. So we have 2 flow paths and 1 surface flow with distinct chemistry. Essentially, you can adjust reaction rates based on what we conceptualize as happening in the shallow subsurface and deeper subsurface. And it works out really, from transition from this very flat concentration discharge relation to these curves that can actually reproduce the data. So which is indicating, it's important to have this different layer of subsurface representing different structure, but also different processes and different reactions. And it happens actually if we're not using the spatial explicit, we're just representing the 2 sides of watershed with 2 grid. It's actually enough to produce these dynamics. So which means the landscape structure is not very important in understanding the dynamic in the CQ dynamic in the stream. And that leads us to think about, about the how the river water chemistry is linked to subsurface structure and processes. If we think about, what do we see in river and stream, and process concentration discharge relationships, and if we think about how water going through the system in different time of the year. Usually, for example, in very dry time, we have the water is relatively low flow. So in this end of the spectrum, you see it's usually dominated by groundwater. So essentially, the groundwater is very much dominated by the deeper layer of the subsurface, which have this high concentration of calcium, but have low concentration of organic material like dissolved organic carbon. On the other side, if you have very wet condition, for example, storms or snow melting time, there's a lot of water, big areas going through the shallow subsurface, which is more dominated by, living material, dissolved organic carbon, nutrients, and so they will flush out a lot of water that reflecting the shallow subsurface chemical signature. So in a way, what we see in river and stream in terms of chemical signature is really reflecting different parts of watershed, how much reaction had happened, and what's the source water chemical composition. And that information essentially echo, a lot of decades of work from in the hydrology field, because catchment hydrology scientists have been asking a lot of questions about for decades in terms of how all this stream water, where is the water coming from, where is the stream water coming from for decades, and they use trace-based analysis measurement to do a lot of work. And this past, this new paper coming out last year essentially summarized at the global scale. The majority of global water, global river flow is sustained by groundwater, which is subsurface water, so about 60%. So understandably, it's reflecting the subsurface environment. So with that in mind, we start to build a third model, which is kind of in between this very simple model versus very, very complicated model, landscape structure. We essentially think about what is role of subsurface structure, and we put 3 boxes following the widely used model HBV. So essentially, it has surface runoff, 3 different flow paths, surface very fast flow, intermediate flow from the shallow zone, and then deeper zone, there's a slow flow. So there's a different flow paths. We can use stream flow to calibrate these different flow paths, but also on top of that, you can build reactions. Depends on how you can representing, different subsurface. You can put in different reaction, different rates, and eventually using stream chemistry to calibrate these data and calibrate these reaction rates. So with that, we can use it to reproduce diverse CQ pattern from, this is one example in Sleepers River, but it's from many of other different places. We can reproduce, we have published a few and also a few in progress. But in any case, this is interesting to show, what the simplicity and complexity of different models. It's really depend on what's the essential information to represent these processes and to capture the key dynamics. It turns out that, it's not only that, this subsurface structure determines these diverse CQ pattern, but also, for example, the deeper respiration in deeper subsurface, the process of, in shallow zone, DOC is being produced when you have a lot of loose microbial material, life materials. It go further, it would recharge into the subsurface, and the DOC is further processed to become dissolved inorganic carbon. And that leads to the very commonly observed, for example, DOC flushing patterns that we always see, in many different places, always increasing pattern, and for DIC, usually decreasing pattern. So when we do this numerical experiment to test these, essentially only when you have deep respirations, it will show the flushing patterns. If we don't include the deep respiration process, then the model output is essentially very flat. So the deeper processing of organic carbon is actually essential to explain these widely observed CQ patterns. And it turns out it's not only can explain the dissolved organic carbon, dissolved inorganic carbon, but also many other solutes, which I'm not going to detail. So that's the second part of my talk. Essentially we think about models, process-based model and processes. For the last few minutes, I'm going to spend time to think about how can remote sensing help, and which maybe we can have some conversation, because I know there's a lot of remote sensing experts here. Hopefully the two major points comes through from the previous parts of the talk, which is, first of all, subsurface is really important, but they are also very poorly understood black boxes, because we have very limited data on these. The other is the river water quality data are very scarce, and I think these are the areas that remote sensing data can help a lot. So, and I could be naive on this. I have to put a disclaimer here. I'm not remote sensing expert at all. So first of all, if we think about remote sensing, right, because there's a lot of remote sensing data for above ground structure, for vegetation, for many different things we can see from remote sensing. And just the above ground property and the below ground property are very much related. So potentially, I'm asking essentially, can we use the rich above ground remote sensing data to infer subsurface structure and variables? I know there's soil moisture being a lot of data being used for soil moisture inference, and also groundwater depths from the remote sensing data, but it seems to me maybe that these variables can be much more extended in terms of thinking about using above ground remote sensing data, because the rich data can be maybe used to infer things that are very poorly measured in the subsurface. And I know in literature, there are some, not necessarily remote sensing, it's a combination of remote sensing data, but all other things, human climate, hydrogeology, a lot of like a suite of different things combined to infer things like groundwater arsenic concentration globally. So there has been application in this direction potentially, and there could be more used more broadly to think about these inference of different type of data. The other one is thinking about remote sensing for inland water quality. My reading of literature is that right now for inland water quality, mostly remote sensing has been used for more like relatively large water bodies like lakes, reservoirs, and large rivers. But this figure is showing that there's many small river and stream. We call them non-perennial rivers, and also intermittent river stream, meaning a lot of these small streams or headwater stream, all these river and stream in arid places. They are very predominant, but they are very small, like narrow. But they have huge impact in terms of affecting the downstream water quality. They have also huge impact in terms of affecting global biogeochemical cycles. For example, the rates in these small streams tend to be higher. The CO2 emission rate tend to be high in these small streams. So there's a lot of importance in terms of having more data in small stream. It seems like the current remote sensing data maybe needs higher spatial resolution if we have missions, more future missions to address these issues. That'd be really nice. For existing work, there's also more, to me, there's more in terms of water quality measurement in terms of publications, but not both of them together. And most remote sensing have been for visible colored water quality, which is understandable, right? There's a lot of remote sensing see what they are able to see. But there's questions about, for example, at least I think it'd be really useful if we think about influence from visible remote sensing to invisible ones. The visible ones including water temperature, colored, dissolved organic matter, turbidity, and all these. But potentially some other variable can be inferred from, or maybe there's other way of using remote sensing to measure this quantity as well. I don't know. This is something maybe a wishful thinking. And I think for water quality, remote sensing could be potentially very useful for understanding dynamics under climate extremes, because climate extreme are the conditions that we need a lot of data. There's huge, big gap in terms of lacking of data under climate extreme, because if we think about doing water samples, we're not going out, logistic is not feasible to go out, take water sample during extreme events like storms and big floods. So we typically tend to have very much lack of data under these extreme, and they're also rare events. They don't happen as much often. So because of lack of data, we have a lot of lack of knowledge. But there are data already showing that, under extremes, the dynamic could be very different from normal non-extreme conditions, which means it's very important to understand and forecasting water quality under extreme. So potentially, with consistent remote sensing data, if there's high enough temporal resolution, we could potentially use these data to understand more under climate extremes. I'm going to stop here and thank you all for listening to me, and I'm happy to take questions.
Thank you, Professor Lee. That was really, really great. I just want to thank you again for starting off our seminar series this semester with such a wonderful presentation. And thank you, everybody else, for welcoming her and helping us start out with a bang. So let's go ahead and start the Q&A. So if you have any questions, everyone is able to unmute themselves. So you can raise your hand and I'll cue you, or if you don't have a microphone or prefer not to, just type it in the chat. I'll read it out loud. Yeah, go ahead, Lars Peter.
Thank you very much, Professor Lee. I'm completely outside the field, so this was extremely interesting for me, especially perhaps part two of the talk, the question of the age of water. This is a very interesting topic, and it mimics what we did in atmospheric science many years ago when we were trying to figure out how old is the air, the stratosphere. I mean, there are a lot of familiarity there. However, I had a comment actually on one of your very first slides. So you were talking about the cost of clean water, and I found that calculation. I would ask if you would share that slide with us because I think it's really fascinating, and I wanted to ask about the source of it. I would perhaps advocate changing the messaging a little bit. I would actually prefer to turn it on its head and say, okay, clean water is non-negotiable. I mean, our livelihoods and our health and our economy and the viability of ecosystems around us depend on it. So it's really about the cost of water pollution, because what you are doing is you are cleaning up something that we did. So I think the messaging is a little bit problematic, but I think the slide is very, very compelling. And again, thank you for a really, really interesting talk.
Thank you. I'm happy to share. I can send you the original paper and yeah, thank you for that. Yeah, I agree. It's kind of alarming because it's so expensive. Yeah.
I can connect you to offline once we're done. I actually have a couple other requests in my inbox for the slides. So I think that a lot of people would appreciate that. Do you have any other questions or comments? And of course, you can just type in the chat if you'd like.
Question.
And Karen.
Yeah. So when you were showing the shallow and deep groundwater, so you've got the biogenic kind of composition in the shallow water, and then you've got the rock weathering components in the deeper water, the groundwater. You were also showing impacts in urban areas, and I work in urban areas and think, well, I think we actually have sort of three layers. We also have the weathering of the urban infrastructure in that environment, which gets stuck up there in the shallow zone when normally it would be weathering processes that are down in deeper zones. It's kind of mixing things up a little bit and it's taking away some of the biogenic component, which is still there in the upper zone. So we're trying to deconvolve those three processes going on in the same watersheds by obviously sampling over a range of spatial and temporal conditions. But I wonder if you had a comment on those effects in urban areas, which isn't really what your focus was when you got to that part of the talk.
Yeah, so the example I show are mostly for, relatively unimpacted sites. We do have three flow paths, so there's three boxes in the model that for urban sites, you're talking about essentially weathering in the surface zone or like the concrete roads and everything. That could be put, for the example we showed for individual sites, we are focusing more like sleepers, rivers, these sites that are natural. So we didn't really, the process in the surface zone is not necessary. But for urban sites, it would be good to have these sites, just like you said, the surface zone could play a major role in terms of determining how they show up in the stream. So this could be in the model's infrastructure, we can add these processes. Yeah, that's that to adjust to the urban environment. Yeah.
And I was just going to make a comment in Newfoundland where we look at, very organic rich soils, but they also have moss growing on top of them, which almost makes another hydrologic layer and a very fast responding one. So we get a lot of the dynamics that you've shown with carbon fluxes, et cetera. But we have to incorporate a very rapidly responding surface layer, which then limits the amount of recharge that goes down to deeper layers, which is kind of surprising if you think of it.
Yeah.
Yeah,
Yeah, so
it's still subsurface flow, but it's moving really quickly through very organic horizons. Yeah.
Right, so it's almost like you could have high proportion surface runoff washing through a lot of things. So that will be kind of depends on the three flow paths. When we have stream flow, that dynamic will show up in the stream. So essentially, you have when we calibrate the model, it will have higher proportion of surface runoff. And if the stream chemistry data is indicating, there's a lot more coming out, we can address certain
Yeah, so you're calling that surface runoff, and it's responding like surface runoff, but it's picking up stuff from the subsurface soil as well. So it's
Right. So you're talking about the very top layers, right? So I mean, we call it the surface, but it's actually more conceptual. So it's really more like fast, very like top layer. We don't know exactly it's above ground or
Right, so-
at the very
all right.
top.
So you're going quick response and slow response water. Okay,
Yeah, exactly. It's more
I'll go
like
with you on that.
fast,
Okay.
intermediate and slow response. Yes.
Thanks. Do we have any other questions before we let Professor Lee continue with our afternoon? All right. Well, thank you everybody for coming to the first seminar of the semester, and thank you so much to Professor Lee again. We will be continuing every Monday until May from now on. Please just keep an eye out for John's emails. I sent a seminar preview email last week. You probably already received it. It's also on our website. But thank you everybody. Have a wonderful afternoon.
Thank you so much.
Thank you.
Yep.